Okay, so as I was saying, Rekha discussed this approximation algorithm yesterday. Remember, to form clusters, to form communities by taking the Fiedler eigenvalue and Fiedler eigenvector, and you, this was approximation algorithm number 2, and you arrange the entries of the Fiedler eigenvector in decreasing order. You do it in descending order of the coordinates, and then you start to take more and more of those coordinates and form this calculate phi of s and look at which one is the maximum or minimum, and that will give you the best version. So I wrote a program for this, and it's on the day 1 folder of overleaf. So here is this example. So again, I take the same Thomason graph on 94 vertices. Oh, it's right. Oh, should I increase the size? Okay, so this is that same Thomason graph. I calculate the. I calculate the Laplacian, which is, remember, called the Kirchhoff matrix, and this is the Fiedler vector. So you see, I mean, the entries are quite all over the place. Many of them are very, very small. You see 10 to the minus 15 and things like that. And what I do is so this sort phi just sorts this in increasing order, and then I find the permutation which converts phi to sort phi, and then I return this permutation, and then I'm looking at the graph. So for instance, just to give you an idea, I'm looking at the first 10 vertices in this permutation. So this is this first 10, and so this highlight graph is really useful tool. So that just shows you where in the graph these vertices live. So what I do now is run this animation. So you can see, we start with one vertex and it slowly builds the whole community. Okay, and for each of those vertices, you can calculate this phi of s, and so you can see how at some point, maybe when it's roughly half, it's somewhere partitioning this way and this way. Right? Okay, so you can change the graph in
What is it doing?
Okay, so I can explain that. So maybe we can take a smaller graph. So let's say Peterson. Okay, so now so you just have to change, so this code just works verbatim. You just change the graph to anything. So here is the Fiedler vector. Okay, so this will be easier to see. You can get rid of that. Now I'm sorting this. So the smallest value is the first one, and the largest value is this one, and in between there are all these things. And now so what this find permutation does, okay, so let's see what it does. I mean, I think it will be easier to spot here. So this is the permutation in cycle notation. Right, so you know permutation cycle, right? So this means 2 goes to 6, 6 goes to 5, 5 goes to 10, etc. So 1 is not here because 1 is a fixed point. So it takes 1 to 1. So that you don't see, which is correct because 1 goes to 1 here. So here you see that so one has to be a bit careful. So the second one goes to the 6th position over here. Okay, that's how it's going. And the 6th one over here goes to the 5th position. No. Okay. Okay, so I keep getting confused. Huh? It's correct?
Yeah, it's right.
So, okay, so I'll go again. 1, 2. So, sixth one goes to the fifth position here, etc. Okay? So, that will give you the permutation which sorts, which takes this to this. Okay? So, that's given over here. And now I just convert that permutation in list notation. Okay? So, it's giving us this. So, 1 is a fixed point, so it stays at 1, etc. So, this now in one line notation, this means 1 goes to 1, 2 goes to 6, 3 goes to 4, etc. You can see 3 and 4 are there. Okay, so here, okay, so that was just to play. Now I should go to, here I should be careful because I should not put 94. I should put length of G or something. Is there a command for size of a graph? The number of vertices?
Vertex count.
Thanks. Vertex count of G if I put, yeah. So I'll just replace 94 over there by this vertex count. Okay. So I can, so forget about that. So let's just do the animation over here. So I'll start off the animation. Okay, so that's what it's going to do. It's just going to collect these vectors. So the red one is S and the other one is S complement, if you remember. We were breaking it into two parts, right? So it's building S according to the algorithm that we saw yesterday, and it's for each S you can write a small code to calculate phi of S. I can do that also if you like. Yeah. So, okay, I just wanted to show you. So, you can play with it. You just have to now change the graph and just run everything serially. It will give you the animation for the same thing. Okay, and I'm running it off of there, so it's updated already. So, okay. So, yeah, one can do much large. Are there like very large graphs one can do in the database?
To calculate this,
Huh.
run the algorithm.
Yeah.
Sure, I mean, you want a large graph just out of this?
Yeah, no, just, I mean, from the graph database is
Oh,
there.
yeah, there are many big graphs for that's a good one. Maybe try,
Like 1,000 vertices or something?
yeah. So you could just type in graph data 1000.
Oh, just put 1,000?
Double bracket 1 and see what happens.
Okay. Oh, so it's just giving me the 10 by 10 by 10 grid.
It's a 10 by 10 by 10 grid.
That's.
But try another one like 10 or something. Hopefully it's better.
Oh, it does not exist.
Try a big one. Oh, it's not part of it. Okay, so maybe 2, 3.
No, wait, what is?
5, 10.
No, it's saying part 10 of grid does not exist.
Yeah.
I'm confused.
Okay, just try it one more.
Something. I'll just do 2. Okay, let me just do graph data 1,000. What does it give? Oh, it's only one graph.
Maybe just one graph. Okay. Maybe try a smaller number than 1,000.
Okay, yeah, here it is. So I'll take something. I don't know, what is a giraffe? What's an antelope? Does anybody know?
There are some interesting. If I want to.
Okay, let's try that. Huh?
It's not sure.
What is
No, you write graph data of antelope. G is all the 10 graphs with all the possible graphs.
No, G is the first vertex. I took the first element.
But try. I think that's a good idea. What Lavanya is saying. You can just try graph data
Of antelope.
colon. I mean,
Within quotes, graph plot within quotes.
No, I want to define. I want to define graph data of antelope.
Yeah, you should be able to complete it.
Okay.
It takes a little time.
Yeah, it's pulling it from the internet. Huh?
There are many antelopes. You have to write antelope, 10, 100.
I think that's not going to work. So if you just stop typing it, so just kill a few letters, and then you should get a.
Like this?
Yeah.
Okay. 510 is here. Oh, I see. I should put, there was some.
10.
Yeah, now 1010 will work. Okay. Wow. No. Too regular will be a cycle.
But the way it's drawn,
Yeah.
it's not regular.
Okay, so let's look at this. So here is a huge cycle. Okay, so I want to animate.
You can make it go slower.
Yeah. So, which one? This one?
Yeah, I think so.
Yeah.
Increase the speed of the animation.
Yeah, I did that. I think the edges go quite far.
Yeah.
I think this one thing is connecting quite a
So
bit.
maybe a homework question is to actually complete this, right? Actually compute the cut or the value of phi of s
Yeah.
for each of these s's, and then take the minimum one. So it's a good mathematical exercise.
Yeah, so for every subset S, one can write. Oh, I don't know, I have 2 copies of this. Delete that.
You could do it as exercise.
Yeah. Phi of S is just the ratio, right? You take the number of edges going from S to S complement, divided by the size of S complement. So you can plot it as it's going from left to right. And at some point you'll find the maximum and you choose that. Did I pause it? Okay.
The first one is inside this one, right?
Did you want to do anything else? I can try and write that code right now, but okay.
No, it's fine.
Yeah.
Maybe we should. Do you want to do exercises now, or should we continue? Like, the one idea is one possibility is to do 2.2 exercises.
Okay.
So proving Farkash, going through all the code stuff. And then on the second page, you prove Farkash, prove category. Some of them we already did, like exercise 5, we did already in class.
Yeah.
The theorem for subspaces.
Yeah, color theory I can prove. If you like.
Farkash, maybe we should start from Farkash.
Farkash proof is complicated, no? My proof is quite.
So shall I do that?
Yeah. Okay.
I can do Farkash and then, maybe the students can do it, but we can talk about.
Okay. So shall I stop this?
Okay, so maybe let's start by looking at, maybe you can read the exercises on the random walks. I read it out earlier. So I think all of that you can try at home. So the random walk exercises are, well, what happens on a bipartite graph, we already discussed in class, that's number 1. Number 2 is to find examples of graphs where the random walk will run much faster if you're willing to start on 2 vertices or 3 vertices or whatever, right? So you need to calculate the spectrum and look for graphs that have very small say, second eigenvalue compared to the first. So let's skip the random walk section. I think this you can try at home. And also to prove the 4-clock theorem using the same idea as the theorem we just proved.
What is the case of equality in that case?
Which equality?
The graph which contains the bound.
Oh, you mean
Converge that exactly converges on that one.
what are examples of such graphs? I don't know. I think I don't know what's like examples where, sorry, maybe I'm not understanding your question.
Or which graph that is equality attains.
Oh, which for graphs is it tight? Oh, I don't know. There's something to, yeah, you should Google it.
No, I mean, this is for all time. This is for all t.
Deregular.
Yeah.
It's no regular time.
Time, t.
Yes. Yes.
It cannot be tight because you want it to be tight for all t.
Yeah, no.
Like that in the middle pattern equality where we went from L plus 1 to n to 1 to n. In that place, that would be a strict inequality, right?
Yeah, you can probably make some improvements on the analysis.
So it might not be possible that this is less than equal to it, might be strictly less than.
Might be, depends on what those extra terms were, right?
Middle, all of those, like 5k translation W is 0 for 2 to n.
That's right.
And for 1, it is strictly positive. That is
Yeah,
the
yeah.
non-1.
So maybe you could write that down. So think about it. So certainly the inequality is okay, but it's possible that you can improve it slightly somewhere. I haven't thought about that. Okay. Yeah, so does that make sense? All right. So I don't really know in terms of what's the best. I mean, I don't even know how to answer that, so I'm not sure. But you can certainly find graphs where like tau 3 is a lot smaller than tau 2, right? So I'm asking you, like, just play with Mathematica and see, are there some good graphs like that where there's a big gap between tau 2 and tau 3, so that you know that if I start on 2 vertices, I will get much faster convergence than the
Initial measure should be uniform.
initial measure?
Should be uniform.
No. We're trying to converge to uniform, right? In the end, you have uniform where you are supported on all the vertices. Initial measure is supported on 1 vertex or 2 vertex or 3 or whatever. That's the L in the calculation, right? So this is something you can play with at home and just check. Maybe for tomorrow, bring a graph where there's a big gap between tau 2 and tau 3 or tau 2 and tau 4 or something like that. Like, just bring some examples so we can show people in class that if you start with 2 vertices or 3 vertices, you'll get much faster convergence than if you start with 1 vertex, okay? So that's really an experimental thing. You have to try this. I think it'll take a while to find the right graph, okay? So that's that. But let's look at the section 2.2, which is the part about Farkas lemma and Carathéodory that I stated, but I never proved. Okay. In the beginning of that whole section, it's just some definitions. So number 1 is, what is a linear combination? That's okay. Everybody sees what a linear combination is. So again, it's the, okay. Then the second piece is cone combination, which we discussed, right? Cone, if you have a collection of vectors, V1 through Vn, then cone combination means a linear combination, sum lambda I Vi, where the lambda i's are non-negative, okay? So that's a definition. And then, so this K is a cone. So K, so let's talk about cones. So if I have K, which is equal to cone spanned by V1 through Vn, then this is the set of all lambda I Vi such that lambda i's are non-negative. Okay, that's what that is. So this is a cone. So maybe the first thing you can check is that if you have something in it and you scale it positively, it's still in it. Do you agree? Maybe think about it for a second. right? So if I have some point x that looks like this, and I scale it positively with some mu, will it still look like that? Will it still be in the set? Is that okay? So this is, okay, so in general a cone, so K cone, if and only if x in K implies that lambda x is in K for every lambda non-negative. This is the definition of cone, just cone, okay? This is a special type of cone where we are saying that it's a set of all linear combinations of finitely many things. So example would have been, I could take this vector, and that vector. This could be my v1, v2, v3. And now if I take the cone span by them, I will get everything that I get by expanding these. So this one, the middle one doesn't matter. And this is the region that I will get as the cone span by v1, v2, and v3, okay? So this is v1, this is v2, and this is v3. This one turns out to be redundant. I didn't really need it. So the cone span by v1, v2, v3 is the same as the cone span by v1, v3, right? And those extreme things are called extreme rays of the cone. So those are necessary, but I don't need that inside one, okay? So we're looking, so first thing to check is that this is a cone, meaning it satisfies this property. Everybody okay with that? Okay, so that's that. And then this has two expressions, right? So what is this? I can also write this as, if I make a matrix, let's call it M, not M, maybe A, which is made up of these V1s through Vn's, okay? Then I can also write this as the set of all. How do I express this? How do we write it in terms of A, the same set? A, X, A, B, X, what? AX? Okay, AX, such that X is not negative. Do you agree? So this is the matrix notation for the same thing, because this is a combination of the columns of A. Columns of A, if you combine them, look like this, but I'm only allowed to combine with non-negative coefficients, okay? So this is one expression for this cone. So the first part, exercise 1, so exercise 1 is asking you to, it's giving you generators of the cone. It's giving you V1 through, in the first example, A is 1, 0, 1, 1, 1, 3, 1, 4. So it's two-dimensional. So draw the cone, and in the next example, it's three-dimensional, 1, 2, 3, 4, 5, and you have to draw the cone. Okay, so 3 dimensions already is going to be very challenging to actually see what's going to happen. Okay, but the 2-dimensional one, can you do real quick? You can try the other one too. See if you can locate the 3-dimensional points, and then you make the cone over it. Okay, I think I tried to choose something reasonable, but let's see. So you can do, this is exercise 1. It's asking you to draw the linear and conical hulls of both. Okay, so the linear span and the conical span. So can you try one of them or both of them? First one is hopefully easy. Second one is probably not so easy, but try it. Yeah. Does someone want to do it on the board? Are you doing the first one? Bishop?
Yes.
Okay. Yeah, actually the first one is already a little tricky. Okay.
So let me do it.
Yeah, you do it. So first one is definitely 2-dimensional. So you got it.
First, maybe draw all the points.
Yeah, draw all the points. And they're vectors, right? You have to draw them as vectors coming out of the origin.
Only 4 points. Okay, so now we want the cone span by column. cone must include the origin. By definition, the cone always includes the origin because all the lambda is equal to 0 means you get the origin.
Correct. It's working, Bishal? So what are your 4 rays? That one. So you have to make the rays, okay? That one, that one, and that one, and the other one, right?
Can you describe the...
Okay, so do you see what's going to happen? Can you shade the cone? What about this? This vector we can expand forever, right?
Yes, ma'am.
Yeah, so what's the cone actually? Yeah.
Kind of square.
And from the and this one also we can expand infinitely long. All of them we can scale positively forever.
So everybody has got the points.
From this one and this one we can just do it.
That's right. So what are the extreme rays of that particular example, part 1? Okay, so 1, 0 is one of the points. And so that's an extreme ray. That'll generate an extreme ray. And then the other one? 1, 4. So the next point is 1, 1, right? And then so you have this ray. And then we have 1, 3.
No, 1. The y coordinate.
Oh, 1, 3, yeah. 1, 3. Okay. 1, 2, 3. Okay, 1, 3. And then we have 1, 4. Okay. So these we can expand forever. All of them we can scale forever. So then do you see the extreme rays? Yeah.
1, 4 and 1, 0.
Yeah, 1, 0 is an extreme ray. This is an extreme ray. And also this is an extreme ray. Okay? So then the cone should be everything that lies between these two things. Okay? Now can you write the inequality representation? So it has 2 extreme rays. So if I were to write it as with inequalities, so remember subspace has span representation and AX equals 0 representation, right? You can write it as a null space of a matrix or the span of a set of vectors. So how do you express this yellow region in terms of inequalities? What do we have to do? So let's also write this as xy such that, so let's say this is the x axis, this is the y axis. So I only wanted the yellow shaded part. Yeah, just give me the 2 inequalities that you have to satisfy, right? To be inside the yellow region. You can write it as a matrix, 2, that's fine. Do you see? Sorry? Yeah, so you need to be on this side of this hyperplane. So that means y has to be what? Yeah, y has to be non-negative. That's giving you this bottom bit. And then what's this one? You have to be on this side of that thing. So what's the inequality? Sorry, just louder please, I can't hear. So this is 1, 4. Y? Okay, so what's the normal of this? Let's calculate the normal. Okay, this is the normal vector to this line. Okay, so if the line is spanned by 1, 4, what's the normal span by? Normal means the perpendicular, right? What, do you see that direction? This direction? Maybe I should put it here. The 90-degree angle to 1, 4. 4 minus 1?
4 minus 1.
Yeah. So this normal is 4 minus 1. Yeah. 4 minus 1, if you dot it with 1, 4, you'll get 0. So the orange little vector is normal to the one side. So now can you write the linear inequality that says that you have to be on the downside of the orange line?
X1 inner product n should be positive.
Sorry, x?
X1 inner product n.
Oh yeah, times the normal, right? So we should get 4x minus y, okay? And then should it be greater equal or lesser equal to 0? Let's think. You want to be on this side of this orange line, right? And if the normal is pointing this way, and you take, so here's the normal, I should properly put it at the origin, and you want to be in this side, so do you want to make an acute angle or an obtuse angle with the normal? It's either acute or obtuse, for sure. Which one? Acute. So if you have an acute angle with the normal, is the dot product positive or negative? It's a cosine, right? The dot product is norm, cosine of the angle between the two thingies. So it should be greater, equal. So this is the dot product. This is the dot product of 4 minus 1 with xy. Okay, so I'm interested in the xy's that make acute angle with 4 minus 1. So the dot product should be greater equal to 0. Okay, so this is the inequality representation of the same set. So so if we were to draw the set again cleanly, we will say, okay, here's my axes, y must be greater equal to 0, so I must be on this side of the y equals 0 line. This is y equals 0, okay? And I must make, I should also satisfy this inequality. This means first you can draw the equality, which is a line, and then pick which side you should be on, okay? So the line that satisfies 4x minus y equal to 0 is this line. It's a line. So this is 4x minus y equal to 0. And then you have to decide which side you want to be on, okay? And you want to be, we're interested in vectors like this, so it should make acute angle with the normal, which is here, okay? So this means that, so if we want to be on this side of this inequality, and now if we satisfy both of them, then we get exactly the cone. Everybody okay? So everything has a generator representation and an inequality representation. Okay, let's go for the three-dimensional example. A lot harder. Maybe not for everyone. Depends on how geometrically.
No, but you have simplified. The question is
Easier?
in such a way that it is simple.
Okay. I made this example a long time ago.
I've chosen all this.
Right. Good point, Arvind. Yeah, so there's something very special about those points, the three-dimensional points. Maybe you notice it first. It's similar to the previous one in some ways.
It's actually even nicer than this.
Okay. So what's special about that configuration, the three-dimensional configuration? Do you see? Last coordinate is 1, right?
So if you take a slice, what do you get?
Y is 0.
What is that? What is that shadow? What kind of shape is that shadow? Draw.
Yeah, so try it. So we have x, y, z. Oh.
Just look at the first two coordinates.
Yeah.
Plot those first two coordinates in the plane. What do they look like? No, don't. I think.
They'll do it?
Let them. No.
Okay.
Just draw it in 2 dimensions. Just draw the. Ignore the last coordinate. This is the same. Just think of 5 vectors with the first 2 coordinates. Just plot those 5 points in the plane. And imagine you are looking from top. What do those points look like? What shape do they form? Square. Square with what vertices?
1 minus 1 minus 1.
Yeah, exactly. So you get minus 1, minus 1, minus 1, 1.
You get a little bit more than that, I think. Okay, what is the shape? Can someone please say? You have 0, 0, and then 1, 1, 1 minus 1, and then
minus 1, minus 1. And minus 1, 1.
okay.
So,
Okay, so we have these. This is just the first two coordinates, right? Now, if you stick the last coordinate as 1, 1, 1, 1, 1, what are we doing to this object? Yeah, we're just like lifting it and putting it on the z equal to 1 plane, right? Okay, so this is the top. This is a view.
this is the top view.
Exactly, and then we go to the z equal to 1 plane, which is like here. And then we need to place this square there. Do you agree? So we had the square down here, which my drawing skills are not so good. Some square down here. That's that picture. And then you got to lift this to this position. Okay? So then, exactly. So upstairs we will get a square. And there's also a point in the middle, but it's not so interesting. And then we have to connect it. So when you connect it, what happens? This sits above the origin, right? So then can you finish connecting? So you should get this, that. Okay? So now can you write the inequality description? So the generator description already showed you that 1 point is redundant. It really only needed 4 points to generate, right? Let's find at least one inequality. Can you find, so what do you want these points to be? So maybe this one is, which one?
Maybe the rays.
Yeah, exactly. I want to get this ray.
Actually, better to get hyperplanes.
Yeah, I'm asking them to compute this side of the cone. Okay? So it's also like 4 inequalities, right? That's bounding the cone. So the sides, right? So how do we get, for example, this blue side? Then by symmetry, you should be able to get all the other sides because it's a square, right? It's completely symmetric. But let's get one of those sides, like this blue side that I tried to. So maybe this is -1, -1, 1, okay? And this one should be then what?
1 minus 1, 1.
Yeah, 1 minus 1, 1, okay? And now can we calculate? And this is, of course, the origin down here. So this blue thingy.
You want the equation for that hyperplane?
Yeah. So what's the hyperplane that goes through the 2 red points and the origin? And then you just have to pick the side. First, let's calculate the hyperplane. What's the normal to this? It's a 3-dimensional picture. Do you see the normal? The normal will like stick out from here. It's perpendicular to the blue plane, right? So the blue plane, if you extend it, it's a plane, right? Goes through the origin.
It's normal to both the vectors.
Yeah, it's normal to both the vectors, but do you remember a way to calculate it?
Wait, what is the formula for a hyperplane in 3 dimensions?
Yeah, maybe that's a good place to start.
Suppose you have what is the structure of a hyperplane? No? Yes? No, but it's in 3 dimensions. Okay, let one person. Yeah, then you say? X1 is
Y plus Z equal to 0. You think it is? Okay, it satisfies it.
by 2.
Okay. What's your name?
Saham.
Saham?
Soham.
Soham. Okay. Okay, Soham claims this is Y plus Z equal to 0. That's what you're saying? It is?
Ax, so he said correctly, the equation for a hyperplane is Ax plus By plus Cz equal to 0.
Correct.
Okay. So for that hyperplane, you just have to. So does the origin satisfy this? Yes. Because
Okay.
something is 0. So now you have to find APC such that these two satisfy.
Yeah.
And remember that if you can, I can multiply ABC by some constant, and it will still remain the same. Right? So twice 2ax plus 2by plus 2cz is also equal to 0. So there is one degree of freedom, but we only have two constraints, so it's okay.
So just start plugging in the
Yeah,
points,
plug
right? 0, 0, 0 already is satisfied, no problem. The right hand side is 0, right? Do you agree? Because it goes through the origin. If you plug in x, y, z equal to 0, you must get 0, right? So the right hand side is 0. Okay, what happens if you plug in -1, -1, and 1? Yeah, so you get, if you plug in -1, -1, 1, you get minus x,
No,
minus a, sorry, minus b plus c equal to 0. So this is coming from -1, -1, 1, and then we had also 1, -1, 1.
A minus B plus C.
Okay,
C equals D.
c equals,
B.
c equals b,
Yeah.
A0.
A0.
a0. Okay,
So now C equal to B. So you get By plus Bz equal to 0. And but B is a non-zero number. So
Correct.
you can just scale it away.
right. So Soham told us that was the answer, and that is the answer. Do you agree? If you call it 2y plus 2z equal to 0, it's also fine. But we might as well call it y plus. Now, which side should we pick? So that's the plane, that's the blue plane extended out, right? But now I have to pick the correct side. I need to be on one side of that plane. How do we test that? Do you know how do we test that? Greater than? Okay, so guess is that it's greater than. How do we?
What's the argument?
Since 1, 1, 1 comes in this,
Yes.
so I can just put 1 plus 1 equal to 0, but that should be 2, right?
That's right. That's right. So you pick a point that it has to, pick a point that has to be on the side you want, plug it in, and see what you get. Exactly. Okay. So you got y plus z equal to 0. Do you think by symmetry you can calculate the rest? What might be the others?
Y minus z.
Yeah, probably minus z. So you can check, there should be 4 of them, right? So that's how we get the inequality restriction.
We must get x plus y. X plus y as well.
Yeah, so let's actually calculate it because it's going to feed into the next exercise.
Okay.
Let's calculate all of them. So this is the method. You see the method, so I won't erase it. So can you just quickly calculate everything?
Write down the other points.
Yeah.
So this would be. Oh, okay. 1, 1, 1.
Minus 1, 1, 1.
Minus 1. These are these 4 points.
Yeah.
So now we look at these 2 points.
Yeah, it's going to be interesting. So one we got 1, it's y plus z equal to 0. Greater equal to 0. Maybe everyone can try a different side so we can crowdsource and get the answer quickly.
Any two of those adjacent, those 1 minus 1s have the same sign.
Okay.
So we can take the one that is equal to 1, and then from that we can get the relation. So for example, in this case, y plus z is equal to 0. That's because the y coordinates was the same, and that we should always take as
Oh, I see. Good idea. Okay.
Y coordinate was the same, eh?
z is 1. So y plus z is equal to
0.
Yeah.
Yeah. So y plus z equal to 0 was satisfied by this point and this point. So that's what he's saying. Like, just look at these two.
Yeah.
And so certainly that's a constraint that's satisfied by both.
Yeah.
And therefore, in this example, that's enough. Okay, so then what are the other ones, Som? Can you read them off?
So here it will be x.
Minus z is less equals to x minus z is less than equals to 0.
Why,
Okay.
why x minus z?
It's 1, 1 and 4.
These two, right?
So z is equal to 1 and x is equal to 1.
Oh, I see. So x minus z. Yeah.
X minus z is greater.
Less than equal to.
Okay, so I want to make it greater for everything, so I'm going to write this. Okay? Okay, good. Let's find more. Minus y.
No, from here.
Minus y plus z is greater than equal to 0.
Okay.
X plus z.
X plus z. Okay. So these are all the inequalities. Can you quickly check? So what works out?
So from here, these two, so I would get y minus z
Mm-hmm.
for these two, and greater than or equal to, and here minus x plus z.
Yeah.
Sorry, x.
It seems right. It's very symmetric. It seems right. Okay? It's okay? Okay, so let's write this in matrix form now. Okay, these are the inequalities. So I want to write this as some matrix times xyz z greater equal to 0. Okay? So I just have to lift the coefficients from this, right? So the first one is 0, 1, 1. Okay? The next one is minus 1, 0, 1. The next one is minus 1, 1, 0 in the front. 1, 0, minus, plus 1, right? Plus 1. Good. So this is the constraint representation. So this is some matrix. Let's call this, I don't know, B.
You call it A.
No, so this is not the same as the other representation. That's what I want to point out. So originally the way the cone started was as the cone spanned by 0, 0, 1, da da da, up to what was it last? Minus 1, 1, 1. Right? This is how it's given. So if we wrote this in the way that we were writing before, that means I'm making column combinations of all these vectors, right? I'm taking 0, 0, 1, 1, 1, 1, 1 minus 1, 1, minus 1, minus 1, 1, minus 1, 1, 1, and then doing x, y, z. But now there's no greater equal to 0. What I need is that x, y, z is greater equal to 0.
No, it cannot be. That cannot be multiplied that way because
Pre-multiplied.
it has to be row multiple. I mean, this has 5 columns. This matrix has 5 columns.
All
So
of
x,
them
y,
rows.
z transpose of this matrix.
No, this is a span. This is not the hyperplane. I mean,
Okay, it's not x, y, z. I need more. So it's,
so 5.
yeah, it's 5-dimensional. Let's call it A, B, C, D, E. Where this, so those are the coefficients, and that has to be greater equal to 0. Correct. Okay? So that is the generator representation of that cone. And what we got before, this is the constraint representation of the cone. Okay? So this will be the set of all x, y, z such that this is greater equal to 0. This is called the constraint representation. And this is called the generator representation. Everybody okay? So these are in general difficult to do, and to transform from one to the other takes doubly exponential time. This is actually a difficult algorithm. It's called Fourier-Motzkin elimination. And you can run this with software. There are lots of software that will convert one representation into the other representation. The reason it's doubly exponential is it's inequalities. So like when you do Gaussian elimination, if you want to derive, if I told you that something is the span of something and then ask you to find the kernel representation, you basically can get it from Gaussian elimination, right? The number of rows don't explode. But with inequalities, you're only allowed to make non-negative combinations, which highly restricts you, right? If I have an inequality of the form, say, A transpose X greater equal to B, and another one of the form C transpose X greater equal to D, the only way I can get a logical implication from these two is to multiply this with some alpha, where alpha is non-negative, that keeps the inequality intact, and multiply this with beta, where beta is non-negative, and then add them. And I will get a new inequality that's a consequence of these two inequalities, okay? So for example, maybe my first inequality was like this, I'm on this side, the other inequality was like this, I'm on that side, okay? That means the common region is this. So to find something that is a consequence means to find another inequality that's also satisfied by the red region, okay? So if I make this kind of combination, what you're doing is you're taking alpha times one linear form plus beta times the other linear form. So you're actually constructing a new inequality that goes through here and points in this direction. Okay? So the red region still satisfies this new inequality. It's a consequence of the first two inequalities. Good? So this is how you work with inequalities. It's a little bit harder than working with equations because the multipliers have to be non-negative. Otherwise, you'll flip the inequality, it changes everything. Good? Harder. Okay, everybody good with this? So we got that. I'm just saying that this inequality that you get by summing the two, right? If you sum the two, I will get alpha A transpose plus beta C transpose times X plus blah, 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 greater equal to alpha B plus beta D. This is a new inequality that I got by combining two inequalities, right? But what's happening is the first inequality was this white thing and this side. The second was this inequality and that side. So the red region is the common region. It's the region that's satisfied by both, right? So when I do this combination, we are combining this linear form on the left with this linear form on the right, similarly these, and you'll get something that is still going to be okay for the red region. The red region still satisfies it. So it'll be some inequality that still contains the red region, right? That's basically what I'm trying to say. So inequalities are harder, much harder than equations, but still not so hard, right? So to show that you can solve a linear system in polynomial time is Gaussian elimination, really easy. It's n-cubed algorithm, or if you like, some fancy complexity, it's like n to the omega, whatever. But to show that linear programming, which has to do with inequalities, is polynomial time, was only solved like 40 years ago, right? It's a much, much harder problem to show that you can find a point that satisfies inequalities. That's much harder, okay? But still it's polynomial time. It's kind of, this description is converting from one to the other is difficult, but otherwise no. Okay, all right, so let's get to the punchline. So I want to introduce the polar cone. All right, let's keep the picture. Okay, so what we just learned is the following, okay? So I can write my cone in two ways. I can write every cone as, let me write it here. So I can write the cone either as the collection of all axes such that x is non-negative, or I can write this as the set of all, I don't know, x's, I guess, such that some other thing, bx, no, this is not x, yeah, this is fine, this is x, or I can write this as, let's change this actually, let's write this as lambda such that lambda is non-negative, lambda is a vector, or you can write it as the set of x's such that bx is non-negative. That's what we just learned. Do you agree? So lambda is like this long vector. So it's either all combinations of the columns of A that are non-negative combinations, or constrained by some inequalities. Yeah? Okay, so now I want to introduce this cone that's called the polar cone, okay? So K with the circle on top. This is the set of all y's that make non-negative inner product with all x's in K. This is called the polar cone. Okay, so let's try this on our first two-dimensional example. Your two-dimensional example was generated by 1, 0 and 1, 4. This was the cone, right? Can you find the polar cone? So I want everything that makes non-negative inner product with everything that's yellow. You can give me the generators, if you like, of the polar cone, okay? So it should make non-negative inner product with every yellow thing. So in particular, it should make non-negative inner product with 1, 0, right? So how far can you take it so that it should make grade A equal to 0 inner product with the bottom ray? It should make only acute angles, right? But the maximum you can go is 90 degrees away from that guy, right? So the polar cone, let's find a color, orange. So if I want to start making acute angles with this base, I can go like this all the way, but the maximum I can go is still here, which is generated by 0, 1. Okay? So that one, is it still okay for everything yellow? So if the orange is making non-negative inner product with everything yellow, do you agree? If you start with the other extreme ray, how far can you go? I still want to make only non-negative inner products. Exactly, acute angle with the slanted line, with the slanted yellow line. So you can start drawing things, acute angle, all the way to? 4 minus 1, exactly. So 4 minus 1 is somewhere here. So this is 4 minus 1, maybe here. Right, okay? So now so if I take everything from here to here, are we good? Everything orange should make non-negative inner product with everything yellow. Any complaints? Does it work? Is that the right picture? It's all right? Don't see it. Not very convinced, right? Okay? All right, I got a bunch of nods. So let's say this is okay. This is the polar cone, okay? So it's everything that makes non-negative inner product with everything yellow, okay? So in terms of this expression, or this expression, can you tell me how to write the polar cone? Let's use either A or B to write the polar cone. The polar cone can be written with constraint representation or generator representation. Do you see if A or B can help us? So yellow is K. And orange is K polar. So what about the columns of A? Are they inside the yellow cone? K is yellow, okay? Are the columns of A inside the yellow cone? Or in the cone K, let's say. Are the columns of A in the cone K? Yeah, right? Because you can use lambda to be just 1 on one column and 0 everywhere else. So the columns of A are there, right? Now everything in the K polar must make non-negative inner product with everything in K, in particular with the columns of A, right? Columns of A are in the cone, so it should make non-negative inner product with the columns of A. So how do we write that part mathematically? So it should be K polar. Let's not write, we don't know what K polar is yet, but I certainly need all the Y's such that it should make non-negative inner product with every column of A. So what's the matrix expression? So here's A. If I want to make inner products with columns, where should we put the Y? Y transpose. So this must be grade A equal to 0. Okay? A is something in this particular example, but do you agree that all these guys have to be in the polar cone? Do you agree? So I will definitely get this containment. Every Y that, or is it the other way? So if you're a Y like this, actually it's this way, right? If you're a Y that makes non-negative inner product with everything, in particular it must make non-negative inner product with the generators, which are the columns of A. Okay, so we get this. Can you show that it's actually equality? If you make non-negative inner product with the generators, then you actually make non-negative inner product with everything in the cone. Let's try it. Okay, I don't want to erase a lot. Okay, so what happens if you are in the cone but not a generator? How do you look? Is it the other way? Why such that?
Because A is a particular case of such X.
Yeah, you get a subset of the cone.
No, because this is less conditions on Y, right? This is saying I just make non-negative inner product with some finite number of things, which is a larger collection than if you want to make non-negative inner product with everything in the cone. You'll get more constraints, right? So it's okay, I think. The inequality is okay. But what happens if you're in the cone but not a generator? How do you look? What's the expression? So let's write it down. So if X is in K, then K definitely looks like, X definitely looks like A lambda, right? So it looks like A lambda where lambda is non-negative, okay? Now, if I pick a Y like this, so what we want to show is equality here, okay? So I have to show that if I pick a Y like this, it'll be okay here. It'll also lie here, okay? So can we try that? So what happens if I pick a Y from this part? So let's pick a Y such that Y transpose A is non-negative. Let's pick a Y like this, okay? And what happens now if you try to do Y transpose X? Can you calculate and see what happens? So Y transpose X, this is linear, this is just matrix algebra now. X is this, okay? X is this. So this is Y transpose A lambda, that's great. Lambda is non-negative, okay? And so Y transpose A is non-negative from here. And lambda is non-negative from here. So what happens when you inner product those two together? Lambda is a column vector, Y transpose A is a row vector. Non-negative, right? So you have a non-negative row vector with dotting with a non-negative column vector. So this will definitely be non-negative. Is that okay? So actually this is the description of the polar cone. So if I know the generator representation of this cone, I get the constraint representation of the polar cone. Good? They switch. This is called duality. So they switch from one side to the other. And then it takes a little bit of work to so can you argue, what happens if I take K polar? So I take everything that makes non-negative inner product with everything that makes non-negative inner product with K. One containment is hopefully clear, right? So everything orange made non-negative inner product with everything yellow. That means everything yellow made non-negative inner product with everything orange, right? So which containment is easy? K is inside this, right? This is easy, but it's kind of a nice fact that it's actually equal. Okay, so it needs a little bit more work. So if you do K polar, you come back to K. Good? So these things are related. So generator representation here is
Is that always true or only for symmetrical cones?
It's only for, it's definitely true for polyhedral cones, not necessarily true for like convex cones. Actually, no, even convex cones biduality holds, I think. So you need some extra conditions to
Equivalent to the Farkas lemma.
yeah, it's a form of Farkas lemma. So now we're going to prove Farkas lemma using this. All right, that's maybe everywhere we'll get. Okay, let's come back to Farkas lemma. Everybody got this? There's a K, there's a polar cone. If you polar again, you come back to the original. So that's it, okay? So can we prove Farkas now? So what is Farkas actually saying? Farkas was saying that either Ax equal B, X non-negative has a solution, or there is a Y that does something. Do you see quickly how, let's see if we can prove that quickly. So Ax equal B, X non-negative has a solution. Can you tell me what this means? Can you express this in terms of cones? So remember, before you told me that if Ax equal B has a solution, that means B is in the column space of A. So let's do the same thing, but in cone language now, right? So what is this saying? Yeah, B is in the cone of what? Columns of A, right? Okay, so B is in the cone spanned by the columns of A. That's what this is saying. It's exactly saying that, okay? So either B is in the cone spanned by the columns of A, or it's not. Do you agree? If it's not, can you then say something in terms of the polar cone? So so let's give this cone a name. Let's call this K. Okay, so either B is in K or B is not in K. Everybody okay with this statement? Okay, so if B is in K, this thing has a solution. Okay, so how do we express this? Let's try to express this in terms of the polar cone. So B is not in K. Okay, so in my picture, B is somewhere far away. So B is not in the yellow cone. So B is like, I don't know, somewhere. This vector, this is B. Not in the yellow cone. It could be there, it could be here, just not in the yellow cone. Okay? Then can we say something about, there exists what that does something. So polar cone makes non-negative inner product with everything in the cone. B is not in the cone. So what must happen?
So Y transpose X should be negative.
Exactly. So that means there must be something in the polar cone that makes negative inner product with B. Otherwise B would have been in the cone. Do you agree? That's it. That's Farkas lemma. Either B is in a cone or not. Okay? So if B is not in K, this is equivalent to saying, I've lost all the whites. Yeah. So this is equivalent to saying there exists some Y in the polar cone such that Y transpose B is negative. Agreed with that? Because if Y made non-negative inner product with B, all the Y's in the polar cone made non-negative inner product with B, then B better be in the cone, right? That's the definition of polar cone. It's just the stuff that makes non-negative inner product with K. Okay, we're very, very close. Now let's write this. How do we write this in matrix language? Y is in K polar. We already know how to write the K cone in terms of generators. Exactly. So this is the same thing as saying Y transpose A is non-negative, and then that happens. Okay? That's it. That's Farkas theorem. So it's very easy to remember, right? It's just saying B is in the cone or not. That's all it's saying. But it gives this really powerful alternative theorem that allows you to certify the lack of solution to a non-negative, a system that has non-negative solution. Is it okay? So please think about this at home if you haven't seen it before, because it's a little bit like magic when you see it first. But this is the foundation of linear programming, this lemma, okay? So this lemma is equivalent to duality, it's equivalent to many, many other fancy things. So usually use one thing to prove the other thing, or one thing this way to prove the other way. Okay, so this is Farkas, and the other one is Carathéodory. So let's maybe just discuss for 3 minutes the idea of how you might prove Carathéodory, right? Carathéodory is saying that if I have a cone that's spanned by lots of guys, so these are the generators. So imagine that we have just, the cone is coming out of the floor, I've just sliced it, I'm just looking at the slice, okay? So way behind the board is the origin. Okay, so then I pick a B, I pick something in the cone, so let's call it B again, okay? And the claim is that this cone is, in our example, this is 3-dimensional, right? The cone is 3-dimensional, I'm looking at a 2-dimensional slice. So the claim is that we can always express this B as a cone combination of dimension many extreme rays. I don't need the 5 or 6 extreme rays I had, 6. It's definitely a combination of the 6 extreme rays, but I can also write it as a combination of 3 extreme rays. It's kind of clear from the picture, right? Okay, so what might be a proof strategy? So suppose not, okay? So suppose this B needs a lot of things. So I write it as lambda I, Vi, I from 1 to K, and K is larger than the dimension of the cone. Okay, suppose not. So I need a lot of things to write this B, okay? Now, if K is larger than the dimension, then what can you say about all those extreme rays that you needed in the combination that you just said is the only thing possible? So let's say, we're saying that, okay, it needs like this one and this one and that one and that one. That's too many, right? That's 4 extreme rays. Let's say we say it needs more than 3, it needs 4 or 5 or 6, right? What can we say about those 4, 5, 6? Like, what must happen? We are in a 3-dimensional space, and I have 4 vectors. They're dependent, right? So that means you immediately get another expression that says that sum of mu I, Vi, is 0 for I from 1 to K. Okay?
By dimension, you mean dimension of the space or dimension of the cone?
Of the cone. Which is, yeah, of the cone. Okay? So I'm just taking a full dimensional cone in all these examples, right?
So in the first one you need lambda i's to be.
Yeah, first one you need lambda i's to be non-negative, correct. In the second one, it's a linear combination, okay? So can you play with this to now decrease to kill off one of the lambda i's? So I have 2 expressions like this. It's like B is equal to, let's say, 2 times V1 plus 3 times V2 plus 4 times V3 plus 5 times V4, okay? So I have that because we are convinced that we need 4 things to write this B. But this, we also know then that minus 5 times V1 plus V2 minus V4 is 0. So we also have a linear dependency on the V's, okay? It's not this example, I'm just making some numbers up, okay? Now do you see how you can play with those 2 things? So the 2, 3, 4, these guys are non-negative, I have to choose them to be non-negative, these guys are not, right? So can you combine this in some clever way so that you still get B equal, okay? So if I add these 2, I'll still get B, right? So I can multiply this with alpha, this with beta. No, let's not multiply this. Just multiply this one with beta. So I'll still get B. So can you do it in such a way that one of the V's will disappear over here? You can choose beta to be anything, right? It's a linear equation. We can scale it with a negative number, with a positive number, whatever. Lavanya. Multiply by 5?
Yeah. Another 5 and add.
And add, okay.
Last term will go.
Okay, excellent. So if I multiply by 5, really? The top one or the bottom one?
V4 will go.
Minus 2 by 5.
No, yeah, so you have to be careful.
You have to be careful. You can't do, so you can scale this up until it gets to 2. Like if I can I can divide this by
Minus 2 by 5.
minus 2 by 5. So I can scale this until it gets here, and then it'll cancel out maybe. Similarly, I can scale this, this, and so on. But you can only scale so that whatever the coefficients you get down here are still not negative. Exactly. So that's the proof strategy. So maybe think about this. So after you do this cleverly, you will kill off one of the V's. So you have reduced the support by 1, and then keep iterating. Keep iterating until you cannot write this linear dependency. When can you stop writing the linear dependency? When we have only dimension many vectors, right? That's the proof. So can you try to see if you can make this formal? Takes a little thought. How do you actually, you can write a formula for how you want to combine, right? So we have this expression, we have this expression. There's a formula for what the beta has to be that you should multiply here so that the next thing will lose one VI. Maybe it'll lose more, but it'll lose at least 1. All right? So that's a proof of everything that we did in the morning. And now let's take a break, and then I'm going to come back. It's a break, right? Yeah. And then when we come back, we'll talk about designs. We'll actually introduce designs.